Hello Year 12. Today we're going to look at Unit 9, which is Group 2. The Group 2 metals you're familiar with already. They're also known as the alkaline earth metals. And we're going to look at the trends in their physical properties as well as their chemical properties, as you might well expect. The elements of Group 2 are beryllium, magnesium, calcium, strontium, barium and radium. And they behave very much like the Group 1 metals, which you learned about during your GCSEs. However, they are far less reactive because obviously they need to lose 2 electrons as opposed to Group 1, which want to lose 1 electron to become stable and have a full outer shell. In terms of their appearance, they all sort of look like classical metals. They're silvery in colour. However, as you go down the group, they get more reactive, and therefore you tend to find on the surface a grey, dull grey material, which is the corresponding oxide. Radium is radioactive. It used to be used in self-luminous watch hands, which is why it's on this particular image here. But it's very, very dangerous being radioactive, and since the 1960s it's no longer being used in luminous watch hands. In fact, people used to get cancer because they used to paint on the radium using a very fine brush that they used to lick to get it nice and sharp, and very sadly lots of people developed cancer. But as we'll see, we'll look at the chemical and physical properties of these very interesting elements in this unit. Let's start off with the physical properties of Group 2. Here's a nice little table. Obviously you don't need to know this specific information, but we're looking at Group 2 in terms of magnesium, calcium, strontium and barium. Obviously we're forgetting about beryllium here and radium here. This information here in this column is the atomic radius in picometers, where a picometer is 1 × 10 to the minus 12 meters. There's also the information about the first ionisation enthalpy, or first ionisation energy, in kilojoules per mole, and then their melting point in degrees Celsius. What I'd like you to do, because you don't need to memorise this data, however, you do need to know the trends in this data. So in a moment, I'd like you to pause this video and draw sketch graphs of each of these properties. So you need to sketch for Group 2 and the atomic radius, the ionisation energy and the melting point. So you want along the x-axis your Group 2 metal, and on the y-axis each of these properties. So I want 3 separate graphs, and I'd like you to explain the trends in those properties. It's worth noting that this is just the first ionisation enthalpy, but the graph that I'll be showing you in later slides is actually the combined ionisation energy for the first ionisation and the second ionisation energy. Please pause the video, have a go at drawing those sketch graphs, and then use those graphs to explain the trends, and we'll run through the answers when you're ready. Okay. Hopefully you've drawn those 3 sketch graphs. Here's mine. This is a sketch graph of the atomic radius in picometers. And what we find is that there's a steady increase in the atomic radius going down the group as there are more electron shells. Indeed, I showed you this visually on the first slide without you realising it. In the upper right hand corner, those blue spheres show you the relative size of the atomic radius. And as you'd expect, as you go down the group, you're adding in more electron shells, so the size of the atoms increases. For the melting point, you actually see a little peak around calcium, but there's a general decrease going down the group as the strength of the metallic bonding gets weaker in larger atoms, as there is more shielding, right? As the electrons are further away from the nucleus, those delocalized electrons, meaning that there's less attraction to the positive nucleus. So the strength of those metallic bonds decreases, meaning that the melting point also decreases. Well done if you got both of those. Oh yes, magnesium is the exception here. That's why I said calcium is a little peak, but magnesium, actually the metallic bonding is slightly stronger than you would expect. In terms of the ionisation energy, This is the first and second ionisation energy combined. Just a reminder in terms of what that means from our lessons way back at the start of the year on atomic structure. The first ionisation energy is the energy needed to remove one electron from an atom in its gaseous state. So we end up with M+ ions. Obviously, having group 2, the group 2 elements actually want to lose 2 electrons to form 2+ ions. So really we ought to be thinking about the second ionisation energy. I didn't want to confuse you with this, so we've just stuck with the first ionisation energy in terms of our sketch graph. And the trend is very much the same. But the second ionisation energy is where you're removing 1 electron from a singly positive ion in the gaseous state. It's not the energy required to remove 2 electrons. But what we find in either case is the ionisation energy decreases going down the group. The reason for that is it's going to be far easier to remove electrons from strontium and barium as the atomic radius increases down the group. That means that the electrons, the outer electrons, are further away from the nucleus. There's more shielding, so they're more easily lost. The attraction to the nucleus is lower. Okay, in a moment I'm going to show you some reactions here in a laboratory. I'm going to show you 2 reactions. First is the reaction of magnesium with steam, and the second is the reaction with calcium and water. Now, ordinarily, I would get you to do these experiments in the laboratory, but obviously, as we're away from school at the moment, I'm going to show them to you in terms of demonstrations. Magnesium, as you'd expect, is less reactive than calcium, so it reacts with water, but very, very slowly. So what I'm going to show you is I'm going to heat up some magnesium, and it's going to react with steam. It will react with steam rather more quicker than it will with water. I'll tell you that the gas that you produce is hydrogen, and you can see in the video I will light the hydrogen jet at the end. What I'd like you to think about is what product will be formed in the reaction of magnesium with water. Then secondarily, I will show you the reaction between calcium and water. Calcium's more reactive, it's further down group 2, those outer electrons are further away from the nucleus, so you'd expect it to be more reactive because those electrons are going to be more easily lost. Obviously it's not quite as reactive as the group 1 elements, but the trend is the same. I would show you strontium and barium, however we're not allowed to keep those because they're a lot more reactive than calcium. However, you can think of strontium as reacting like sodium and barium reacting like potassium because their reactivities are similar. What I'd like you to do whilst you're watching the video is just to make some notes of each demonstration, and once you've watched the demonstration, I'd like you to pause the video and I'd like you to write down the 2 equations. One equation for the reaction with magnesium and steam, and one equation for the reaction of calcium and water. Please can you include state symbols? We've got some mineral wool here that's soaked in water, some magnesium ribbon here which I've gone over with some emery paper so that the oxide layer has been removed, and then we've got a delivery tube. All of this is in a boiling tube. So what I'm going to do is I'm going to heat up the water so that we should see some steam coming out the end here, and I'm then going to start heating up the magnesium, which should get really, really bright, but it does take a bit of time to get warmed up. So I've just warmed up the water a little bit. It's starting to go, it wants to. And hopefully you can see underneath, if I lower the clamp stand a little bit, that the glass has been warped because it's melted, it's got so hot. In goes the calcium. Let's try and nab it quickly. So it's fizzing away in the boiling tube and it's rapidly producing a gas. So let's take a splint in readiness. You can perhaps see that something's also happening to the water as well. It's changing colour. That's probably enough gas for what we need. Got a lit splint here. Just wait till it completely fills the tube. And a rather pathetic, but nevertheless some form of a squeaky pop. So you can see the calcium still fizzing away here in the beaker. I'm going to add some universal indicator, and you can see that it goes a dark blue colour, about pH 10, maybe pH 11, showing that you formed a relatively weak alkali calcium hydroxide. Those were our two lovely demonstrations. Just to remind you, I'm after the balanced symbol equation for both of the reactions that we've just seen, including state symbols. Please pause the video and do that now if you haven't already done so, and we'll go through the answers when you're ready. Okay, we've talked about the trend in the reactivity with water. Hopefully what you've got here is that magnesium reacts with water, or in our case actually steam, to form magnesium oxide and hydrogen. And so you should have magnesium solid reacting with steam, which is H2O in the gas phase, to make magnesium oxide and hydrogen. Well done if you got that, because actually what you'd expect is that you would form magnesium hydroxide rather than magnesium oxide. However, all of the other elements in group 2, when they react with water, will form the corresponding hydroxide. So calcium reacts with water to form calcium hydroxide and hydrogen. Indeed, in the video, you saw the calcium hydroxide as being a white, sparingly soluble solid. So you'd see little precipitate, a white precipitate forming if you were watching closely. And obviously I demonstrated that it was hydrogen gas from a rather pathetic squeaky pop. In the previous demonstration, magnesium oxide is formed because it's white. You'll probably have a small amount of magnesium hydroxide there as well. You may have even written out the balanced equation for that, realising that you need more water for that to occur. And hydrogen is, I obviously told you, was produced because you can ignite the hydrogen gas coming out at the end. These are called the alkaline earth metals, as they make alkalis. You saw in my demonstration calcium hydroxide solution. It's sparingly soluble, barely soluble, so as a result it will turn universal indicator blue. It is a relatively weak alkali. Indeed, the more reactive elements like strontium and barium dissolve far more easily, so they make much more stronger alkalis. You know, you'd be looking at sort of pH 13 or 14 for strontium and barium. We need to therefore think about the trends in the solubility then, and this is on the front of your unit guide. The hydroxides, you've got magnesium hydroxide, calcium hydroxide, strontium hydroxide and barium hydroxide. Remember that you need to know the formula of these. Hydroxide has the ion OH-, whereas all of these guys are in group 2. They're going to form ions with a 2+ charge, which means that in order for that charge to cancel, you're going to form magnesium hydroxide MgOH2, because you need 2 hydroxides to cancel out with a 2 positive charge on the magnesium. In any case, in terms of the trends of the solubility, as you go down the group, the solubility increases. Magnesium hydroxide is barely soluble at all. Calcium hydroxide is sparingly soluble, and these guys are incredibly soluble. So the solubility increases as you go down group 2. In terms of the sulfates, the trend is the other way around. For barium sulfate is very much not soluble, whereas magnesium sulfate is incredibly soluble. Barium sulfate, you may recall from your GCSE studies, is a precipitate. It's a test actually for sulfates. If you add barium chloride to things, it will form barium sulfate. So you know that you've got sulfate ions there, and this is a white precipitate. That's the way that one can remember this particular trend. If you remember that it's the opposite for the hydroxides and simply remember the hydroxides, this becomes very, very straightforward. So that would be my tip. Remember that the solubility of the hydroxide increases down group 2, and then you can simply remember that the sulfates, it's the other way around. The solubility increases up group 2 or decreases down group 2. Uses of group 2 hydroxides then. Group 2 hydroxides are incredibly useful. Certainly if you've ever had a stomach upset, you may have used milk of magnesia without realising it. It's a very mild alkali that neutralises stomach acids. And you know from the previous situation that this is sparingly soluble. So it sort of dissolves in water, and therefore you can make a solution of it which will ease stomach pain, although really it's sort of a powdery paste, really more than a solution, because magnesium hydroxide is barely soluble. Calcium hydroxide is more soluble than magnesium hydroxide, as we know, and this is why it forms a substance called lime water, which you'll have used in your experiments in school previously. And you'll notice that it's a very, very sort of, it looks sort of colourless, but if you look very closely at a bottle of lime water, you'll see that at the bottom there's actually a precipitate of undissolved calcium hydroxide. Now, lime water, and lime calcium hydroxide, as a powder, is spread on soils that are too acidic. It neutralises those soils to make it more favourable for plants to grow. And indeed, you'll notice from this rather fantastic photograph, clearly from the 1980s or maybe early 1990s, from a textbook that I found, this student is blowing bubbles of carbon dioxide from her lungs into lime water, making it go cloudy, because the calcium hydroxide is reacting with carbon dioxide to form calcium carbonate and water. So you actually form crystals in here of calcium carbonate, of marble, which is why the solution goes cloudy. You need to know uses of group 2 sulfates as well, which is why you need to understand their solubility. Calcium sulfate is an immensely important material which is used in the production of something called gypsum, which is otherwise known as plaster of Paris. So it's used all over the world in wall coverings, in what the Americans would call drywall, or what we call plasterboard. And indeed it's used in making plaster for walls, coating. So all of our buildings have plaster of Paris on the surface to give us a nice smooth insulating surface in our buildings. And indeed it's universally recyclable. You can recycle it as many times as you like, which is what makes it a really interesting material from that perspective. Barium sulfate has all sorts of medical applications. It's very, very insoluble in water because, as I've explained previously, you can therefore use it to test for sulfates. If you take a solution that contains barium ions, such as barium chloride, you can add this to a sulfate, and what you'll see is that you'll form a white precipitate, indicating that you have a sulfate there, because you form barium sulfate as a precipitate because it is insoluble. Barium sulfate is also used in barium meals. Because barium is a very large ion with lots of electrons, it absorbs X-rays rather well. So X-rays don't pass through barium compounds very easily, so they show up as white splodges, as white things on X-rays. So it allows you to image soft tissues that ordinarily you wouldn't be able to image because the X-rays would pass straight through. So they're used to image things like the intestines and stomach to see if there are any problems with your digestive system, hence the term barium meal. What happens in the test for sulfates then? Well, we've gone through this already verbally, but it's nice to have a go at writing down an equation. Barium chloride is added to another substance suspected to contain sulfates, let's say sodium sulfate in this instance. Remember that the charge on a sulfate ion is 2-, so that means you need to have 1 sulfate and therefore 2 sodiums, because sodium is in group 1. And what happens is that the barium chloride will react with the sodium sulfate to form barium sulfate and sodium chloride. Barium chloride is aqueous. Sodium sulfate is also aqueous, dissolved in water. And barium sulfate is that precipitate, is a solid. And you also form sodium chloride, which is aqueous. But what's actually happening in terms of the ions? What I'd like you to do in a moment is to pause the video, write out the individual ions that are involved in this particular chemistry, and see if you can work out what's happening as part of the equation. Because there are actually some spectator ions involved in this equation that don't undergo any change. They don't undergo any chemistry at all. See if you can work out the overall equation, the simplified ionic equation for this particular reaction. Hopefully what you've worked out is that the chloride ions are unchanged and the sodium ions are unchanged. So as a result, we can write a simplified ionic equation where barium ions, barium 2+ aqueous, will react with sulfate ions, SO4 2- aqueous, to form barium sulfate, which is a solid precipitate. In other words, both the sodium ions, Na+, and chloride ions, Cl-, remain in solution. They don't undergo any sort of reaction. They're so-called spectator ions. They watch and don't take part in this particular reaction. But this is the overall reaction if we had to write it out as an overall balanced equation. However, this is the ionic equation. This is the actual chemistry that takes place. So often there are exam questions, and you'll have experienced these, have got experience of this from GCSE, in terms of questions asking you how to prepare a pure dry sample of something like barium sulfate. And indeed, apologies guys, if it were in the laboratory, we'd have a go at this particular experiment, but unfortunately we can't. But I thought I'd talk you through it in any instance, because there could be a lovely 6-mark exam question on this. But you take 2 solutions. You take barium chloride, BaCl2, which is aqueous, together with magnesium sulfate as an example. So here you're going to form barium chloride and obviously magnesium sulfate. Magnesium sulfate will remain in solution. Magnesium chloride will remain in solution, whereas barium sulfate will be the precipitate. So you'd mix the 2 solutions, usually in some form of conical flask, or you could do it in a beaker, and you'd have some form of precipitate formed. You then filter that through a usual filter funnel setup. I wish I'd have shown this with a conical flask, but you can do it going into a beaker. A conical flask would be easier as you wouldn't need to clamp your funnel here. And what you'd find is that your precipitate would be barium sulfate, whereas the filtrate, the material that washed through, would be magnesium chloride. And you'd need to wash the solution carefully, because your spectator ions would remain in solution. So as an equation, if the exam question asked you for an equation, it will be barium chloride, BaCl2, aqueous. Remember, you need 2 chloride ions because chlorine is in group 7, barium is in group 2. You'd react with magnesium sulfate Charge on a sulfate ion is 2 minus, charge on a magnesium ion is 2 plus, so it's just MgSO4 is aqueous. This forms your barium sulfate, which is your precipitate. I've tried to colour code it here for you to make it clear. And you'd form your magnesium chloride, which would be a filtrate, the thing that you wash down into it. Why do you need to wash the precipitate carefully? Pause the video, have a little think about it, and when you're ready for the answer, press play again. Okay, the answer is why you need to make sure that you wash your precipitate carefully is because if you don't wash it, then you'll actually have a mixture of barium sulfate and magnesium chloride in here. Because unless you wash through the magnesium chloride, which is aqueous, so it forms your filtrate, then you'd end up with a mixture of barium sulfate and magnesium chloride once it was completely dry. And to completely dry it, you remove the filter paper from the filter funnel and either place it on the side on a window ledge in the laboratory, or alternatively what you would do is you'd place it into an oven to allow it to dry in the oven. And that's pretty much it, guys. Group 2 is just a short and sweet little unit. Don't forget that you can access the unit guide and homework booklet on the VLE. I will put links up on the Microsoft Teams platform to allow you to access that. It's just a very short and sweet little unit. We'll give you a little end of unit test after you've had the time to digest this and have a work at some of the chemistry. This is a lovely little image. You can find all sorts of these different images at a website called Compound Interest, which can be found at www.compoundchem.com. Yes, a lovely little summary of all of the Group 2 chemistry that we've discussed. Thanks ever so much for watching and listening, and I'll see you next time.